Now today's topic of discussion is to obtain the equation of magnetic field on the axis of circular current loop. Now this figure shows the circular current loop which is placed in YZ plane. You can see this way. This is Y axis, this is Z axis, and it is kept in this YZ plane. Okay, and the current flowing through this loop is I. Okay, and the radius of this current loop is R, and x axis, as you know, it is perpendicular to y and z axis, and we want to find out the magnetic field at this point P, which is at distance x from the center. Okay, from the center the distance of this point P is x. Okay, so the loop is placed in YZ plane with its center on the origin O, and the radius of the loop is R. Okay, now the x-axis is the axis of the loop, that you can understand, and we want to calculate the magnetic field at point P on the axis, and the distance of this point P is x from the center of the loop, which is on the origin. Okay, now we want to consider a conducting current element dl of the loop, and the magnitude of the magnetic field dB, which is produced by this dl, is given by the Biot-Savart's law. Okay, and this is the formula of Biot-Savart's law. We have taken a very small current element dl of the loop. Okay, and this magnetic field is given by this formula dB is equal to mu 0 upon 4 pi I dl cross r upon r cube. This is the magnitude of magnetic field produced by a small current element. Now this I am showing it separately. Okay, try to understand this with the help of this particular arrangement. Okay, see here there is a black colored current loop, so you can understand this black colored current loop. Okay, this is placed flat on the surface. You can just turn your mobile on the other side, then you can see it how it has been shown in the other figure which we had. If you place it your mobile say vertical, then you will be seeing in the way which is shown in the figure. Now see, here the current loop is taken, but you can see this is the current loop. Okay, and the current is flowing in this particular direction. Okay, so this is the direction of flow of current, and the current flowing is I. Okay, now the radius of the loop is R. Okay, so let me show it by a different color for you. Okay, this is the radius, okay, which is R. Okay, so this much is clear to you. Now just try to understand it this way. Okay, so this is the loop which is shown here. Okay, and now I am turning it on the other side. Okay, where you can see the current element. Okay, so just I am turning it here. Okay, so this is the current element which I am showing. See, the current is in which direction? In this direction. Okay, so this is the current element which is taken. It has been magnified. It is an infinitesimal current element, and the current element is denoted by dl. Now because of this current element, the magnetic field is produced on the axis. Okay, so let us see. This is current element which is shown by this green colored straw. Okay, and we want to find out the magnetic field at this point P. Try to understand, this is the point P where we want to find out the magnetic field. Okay, now so this is the point P where we want to find magnetic field. Okay, so that has been shown with the finger. Okay, and this blue colored straw, try to understand now, this blue colored straw which is showing you here, the distance of that point P. Okay, let me draw it again for you. Okay, this blue colored straw is showing the distance of that point P from that current element, that is dl. Okay, this current element is this side. Okay, and the distance of this point P from current element is r, or we can say position vector of point P, where we want to find out the magnetic field with respect to current element is r, that is small r, and the distance of this point P from the center of the current loop, center of the current loop is on origin, and that distance is x, and this is the radius of the current loop. So you try to understand it in a 3D way. Okay, so now, as you know, our Biot-Savart's law, that small magnetic field dB is given by mu 0 upon 4 pi. Okay, I try to understand now dl cross r upon r cube. So now that magnetic field which is produced is having its direction depending upon dl cross r. Now how to take dl cross r? Now this is your dl, okay, and this is your position vector r. So you have to rotate the dl in the direction of vector r. A cross b માં શું કરીએ છીએ? We are rotating vector a in the direction of b, and the right hand screw advances in a particular direction when you rotate one vector in the direction of the other vector, and the direction of the advancement of right hand screw gives the direction of resultant vector. So now you are rotating dl in the direction of r. So you can see that the screw will advance in this particular direction. Okay, that is shown by, or it will be advancing in the direction perpendicular to the plane formed by dl and r. Now see, dl and r is forming the plane which is shown by this brown color cardboard. Okay, so perpendicular to this, the vector of dB or small magnetic field will be, okay, or you can take the other way, dl is rotated in the direction of vector r and perpendicular to it, that is this direction, yellow colored straw. This yellow colored straw will show you the direction of the magnetic field dB. Okay, now see, that is easily visible. See, this is blue colored straw. Now this is green colored straw which is giving you IDL. Okay, so that blue colored straw is giving you the position vector of the point P. Okay, now we want to find out the dl cross r. Okay, so that vector r is shown again. Okay, now see, it has come in a proper position. Okay, where you can easily see the dB. Okay, dB you can see. So this is again IDL which is shown, this is vector r. Okay, now yes, IDL is rotated in the direction of vector r, and that will give you the perpendicular to the plane formed by dl and r. Okay, perpendicular to the plane formed by dl and r. Okay, it will be, you can see, okay, it is rotated in anti-clockwise because the vector dl is rotated in the direction of this vector which is r. You can see, okay, that is rotated. Now you can also see that dl and r are perpendicular to each other. Okay, so angle between dl and r is 90 degree, that is also visible from this model. Now perpendicular to this plane that is formed by this vector dl and r. Okay, so you can see, yes, that yellow colored straw. Now you can see yellow colored straw, okay, which is perpendicular to the plane formed by this two. Okay, this yellow color shows the direction of dB, that is magnetic field. Okay, so this is very clear. Okay, now we move further. Okay, so dB vector is showing you the direction of this magnetic field produced by this current element of dl. Okay, you can easily see it. Okay, yes, so now you can see this part also. Okay, so where the magnetic field is produced, that is shown here. It is yellow colored straw which is showing you the magnetic field. From this it is very clear, you can see. Okay, easily it is visible, it is seen. Okay, yes, this is your green colored current element, that is, we can say it is current element IDL, and this is vector R, and this is the direction of magnetic field which is perpendicular to this plane formed by IDL and R. Okay, so here this angle, if you can see, must be 90. Okay, perpendicular to the plane, that is why this angle will be a 90-degree angle. Okay, this angle will be 90-degree. Okay, so that is visible to you. Okay, now we move further. Okay, so it has been shown here. Okay, now see, this side you come where we were earlier. Okay, here you can see that this vector r, which is a position vector of this point P, okay, that is making an angle here. This angle is theta. Now this angle is theta, so, and this is 90-degree, you can see. So this angle has to be 90 minus theta. Okay, 90 minus theta it has to be. Okay, so that is tried to explain here. Okay, that this is this angle is theta, and here which I tried to explain was 90 minus theta. Okay, so this is 90 minus theta. Here this angle is 90. Okay, so here this angle is 90. Okay, and the distance of this point P where we want to find the magnetic field is x. Okay, so that is very clear where we want to find the magnetic field, that is this distance is x. Okay, this angle is 90 minus theta, that can be understood easily. Okay, so that angle which is shown here is 90 minus theta. Okay, now this whole angle, you can understand, is 180. Okay, the whole angle is 180. You can see, slightly back I am taking. Okay, now you can see this total angle is 180. Okay, and this is your 90 minus theta. Now this is the magnetic field which is produced. Now see, this angle you can see it is 90. Okay, and this angle is 90 minus theta which I have shown. Then this much angle, let me show it with a different color. Okay, this much angle which I have shown with the blue color has to be theta. Have you understood? 180, total is 180 minus 90 minus theta minus 90, this angle. and this angle I have subtracted from 180. Total is how much? 180. So I am subtracting this 90 minus theta and I am subtracting this, then I will get this much. And you can see that it becomes 180. Then this is also minus 180, 90 and 90 will become 180 plus theta. So the upper angle which I tried to show, okay, this particular angle I am talking about is theta. So that must be clear to you that this angle which is made is theta. So this is theta, this is your 90 minus theta, and here this is 90, okay, and this particular angle becomes theta, as this is also 90. This is your 90 minus theta. Okay, so this dB vector, this I want to show. This dB vector which is shown here is making an angle theta with this axis. That I have shown in that figure. Okay, here in the original figure I showed, okay, that this particular angle, okay, which is made by this dB vector with this axis is theta. So now dB cos theta component, dB cos theta component will be in x direction, and dB sin theta component or dB perpendicular will be in this direction which is shown by me, okay, dB perpendicular. Okay, now similarly if you take another ideal in opposite direction, okay, here if you say you have taken ideal, then other, if you take this ideal component opposite to this ideal, then the magnetic field will be in this direction. Its dB cos theta will be in this direction, and dB sin theta, that is dB perpendicular, will be opposite to the earlier dB perpendicular. So these dB perpendicular are cancelling out each other's effect, and only dB cos theta components are responsible for the magnetic field at this point P. Okay, so we now can move further. Okay, here this angle again, okay, here this angle which I have shown is theta, okay, this angle is theta, that is shown here, and here the angle made by this vector r with this radius is also theta, okay, that has been shown in that particular different video. Okay, now this figure is clear, so we can find the value of this r square easily with the help of our Pythagoras theorem. This becomes the hypotenuse for this particular triangle. So r square is equal to, this is your x and this is capital R. So you can easily find r square is equal to capital R square plus x square. Now it is all mathematics. Okay, dl and r are perpendicular, that I have shown in the model. So dl r sin 90 it becomes dl into r. Okay, so our equation which I have written for the Biot-Savart's law can be easily understood now. Okay, it is very easy to understand. Mu 0 upon 4 pi remains as it is, I dl r sin 90. So it becomes dl into r upon r cube. So one r will be cancelled out and you will have the simplification to be mu 0 upon 4 pi I dl upon r square. Now substitute the value of r square. R square we are having capital R square plus x square. Instead of this small r square we can write this. Okay, so next equation can be easily written. Okay, instead of this small r square, okay, this value of small r square we are putting this r square plus x square, this much we are writing. So this new equation we are getting. Okay, now the direction of dB is shown in the figure that I explained. Okay, this is the direction of dB, okay, you can see the direction of dB easily. This is the direction. Okay, now it is perpendicular to the plane formed by dl and r that I explained. Okay, now the new thing is that it has x component dbx and the other component is db perpendicular, which is perpendicular to x axis. Okay, and db perpendicular are getting cancelled out due to other dl which is on the opposite side of the dl which we have considered. Okay, so the contribution due to diametrically opposite dl element, okay, which is shown in the figure, so they are getting cancelled out too. dB perpendicular components due to dl are cancelled by the contribution due to diametrically opposite other dl element, which is shown here. This is your other dl element. Okay, this is the other dl element which is cancelling out the dB perpendicular component. This dB perpendicular component is because of this dl, and this dB perpendicular component is due to this another dl which is diametrically opposite to the dl which we have considered here, this side. So they are cancelling out each other effect. Only dB x components are contributing towards the magnetic field produced at point P. Okay, so that is easy to understand once you see this 2-3 times. Thus only x component survives. The net contribution along x direction is nothing now because of dbx, and that is db cos theta. So whatever db is produced, dB cos theta components are responsible for magnetic field at point P. Okay, now calculation part, again the figure is there to refer you again and again. Okay, so that figure I am putting it again and again. This is the distance x. Okay, this is dl which is producing dB this side, this dl is producing dB this side. Only dB x component are contributing towards the magnetic field at point P. dB perpendicular are getting cancelled out, and dbx is nothing but dB cos theta. So dbx is nothing but dB cos theta. Okay, so from figure you can take cos theta now easily. Okay, how to take cos theta? It is adjacent upon hypotenuse. Now here I tried to explain that this angle is theta, that I have shown you in that model also. Now cos theta, if you want to find, then it is adjacent upon hypotenuse, and this small r is nothing but, as such r square we have written, it is r square plus x square. So small r can be written as under root of r square plus x square. Okay, and that is why cos theta can be taken to be adjacent, that is capital R, upon this small r. So that can be written as capital R upon under root of r square plus x square. Okay, thus equation 3 to find the total magnetic field can be, because now the value of dB is because of dbx component. Try to understand. The value of dB is because of only dbx component. So we are integrating it. So all the dbx components we have to take, and dbx is nothing but dB cos theta. Now dB we are having, it is mu 0 idl upon 4 pi r square, that you are knowing, that you must write down somewhere. Okay, when you are understanding this, you go on writing in your notebook. Mu 0 upon 4 pi, it becomes idl upon r square. Now instead of this r square, we have already written capital R square plus small capital R square plus x square. Okay, that we have already written. So try to understand this way, that this dbx integration dbx is db cos theta, and db we are having it is mu 0 upon 4 pi idl upon r square plus x square and this cos theta. Okay, so again I am explaining, try to understand. See, this db which we have already written, we have that value of db, and that db is what? Mu 0 upon 4 pi idl upon r square plus x square. This we are having into cos theta, just we have done. Okay, so dbx, the dbx is db cos theta, and db we are having the value mu 0 upon 4 pi idl r square plus x square idl upon r square plus x square into cos theta. Now cos theta we have to substitute here. Okay, so what will happen if you place that value there? Okay, just we have to multiply by that particular value. Okay, so this value I have placed here instead of cos theta, so you can see it here. So here there is 1 power, here there is half power, so raised to 1 plus 1 half, that is 3 by 2 it becomes. So the new equation, other all remains as it is. See, other all will remain mu 0 I dl into capital R upon 4 pi. Okay, so it becomes this way, mu 0 I dl R upon 4 pi, then it becomes r square plus x square raised to 3 by 2 it becomes. Okay, so the new equation is like this, mu 0 I r, okay, dl is taken in the integration, 4 pi r square plus x square raised to 3 by 2. Now if you take all the dl, all dl, if you calculate all the dl will together make the circumference of this circular loop. So instead of this dl we can write now 2 pi r circular circumference. Okay, so it is written in the next equation. Here dl is 2 pi r, so instead of that integration dl we have written 2 pi r. Okay, and there will be a cancellation of pi. Okay, this pi can be cancelled out. Okay, and this 2's r can be done. Okay, so it becomes mu 0 I into r square, this 2r will become r square upon 2r square plus x square raised to 3 by 2. As this is the integration of the component in the direction of x axis, that is x component of magnetic field, the vector form. Okay, this is the value only. This is fifth equation gives you only the value. The direction is in the direction of x axis, so magnetic field will be in the direction of x axis. Okay, because the x component is in x direction. Okay, the component of this magnetic field is in which direction, that is shown. In which direction the component is in this direction. So magnitude which we have found, that is okay, but the direction will be in the direction of x axis, and that is why it was multiplied by I cap. Okay, so the final equation will be having I cap. Okay, our magnetic field is in the direction of the x axis, and that is why, okay, here I cap is multiplied mu 0 I r square upon 2 r square plus x square is to 3 by 2 into I cap. Okay, magnetic field at the center of the loop. Now if you want to find the magnetic field at the center, then at the center when you come, then the x becomes 0. Try to understand. If you bring this point P here at center, then x becomes 0. So in that equation which we have derived, we have to write, instead of x we have to write 0. Okay, so the equation can be written easily. Here if you write instead of x to be 0, okay, instead of x you write 0, so it becomes mu 0 I r square upon 2 r square raised to 3 by 2. Okay, so this becomes 2 2s r, it becomes, and then this becomes r cube, and r square will be cancelled out with this, and r will remain in the denominator. So mu 0 I upon 2r I cap will be the equation. Mu 0 I upon 2r I cap, that can be the equation. Okay, for n loops, this is only one loop which was taken. It was having only one turn. If you have n turns like this, one on the top, okay, then this magnetic field at the center will become n times stronger, or capital N times stronger than the magnetic field produced by single ring. Okay, so this is all about the magnetic field produced by a circular loop. Okay, hope you understand it properly. Ampere circuit law we shall continue next time. Okay.